Okay, so good evening, good afternoon, and good morning, wherever you are in the world. And I think for astronomers, this is really important because time is relative. So obviously, it's also good to say those three good days, I would say, or greetings to everyone. My name is Marek Łukasik, and I'm Vice Rector for Development and Cooperation of Pomeranian University in Słupsk. And it's my pleasure to greet you tonight, everyone, and to basically introduce to you our guests today. Now, before I do that, I will just very briefly present the program itself. The program within which this event is possible is called A Plus Lectures. And those A Plus Lectures is our project that we organize as university as our third mission. So this is our public outreach program, which aims to basically spread the scientific knowledge, research activities or research results to the general public, but also obviously to our students and to all the people interested. Today, a very interesting topic that's into astronomy and astrobiology. Let me introduce Dr. Michaël Gillon of the University of Liège, if I'm not mistaken. Good afternoon, good evening.
Good evening. Nice to be
And
here.
thank you so much. And let me say, I'm really grateful that you have accepted our invitation to deliver this lecture tonight. And let me also introduce Dr. Krzysztof Czart of European Southern Observatory, who will be the moderator of today's event. And well, let me say that I will join you later on just to summarize the event. And in a minute, I will give the floor to Krzysztof. But before I do that, maybe I will just say a few technical things. I will tell you what to do with your questions. Now, obviously, during the lecture today, you may have different questions. There is a chat box, there is a chat window that you can see on your right. Now, you should put your questions there in the chat. And once you have put your question, Krzysztof will later on, towards the end of the lecture, will read out the questions. There is some message coming in that there is this echo. Michaël, if you can mute your mic for a minute, thank you, just for a little while. Thank you. So thank you so much. Thank you, Maria. So just to tell you, so you ask your questions in the chat box, and Krzysztof, the moderator, will later on read the questions out, and Michaël will be able to answer those questions. Now, we will read those questions out because people who are joining us through YouTube are not able to ask those questions through this chat, but let me remind you all that you can use the YouTube chat as well to send us messages. So there is this public chat that you can see on our channel. We have 23 people joining us through YouTube, and I think many more are coming in. Thank you for joining us tonight. And please don't forget to send your questions there, but also probably greetings, comments, and any feedback that you may have. So that's all about the technical issues. So let me give the floor to Krzysztof Czart, Dr. Krzysztof Czart of European Southern Observatory. Thank you for agreeing to moderate this meeting. Thank you.
Good evening. Thank you for invitation. I was asked to shortly introduce European Southern Observatory because some discoveries by our speaker are related to ESO telescopes. So let's start from that. What is European Southern Observatory? It's in short, it's called ESO, or in Polish we call it ESO. It's an international organization whose aim is observing sky with large telescopes from ground, not from space, but from ground telescopes. It was established about 60 years ago by 5 countries. Among them was Belgium, so country of our speaker. Later, more countries joined, and Poland joined a few years ago in 2015. But at that time, 60 years ago, there wasn't too much telescopes in Southern Hemisphere, and Europe is in Northern Hemisphere, so it does not have access to some parts of southern sky, for example, to center of Milky Way. So Europe wanted good observatory in opposite side of a globe. And finally, a few countries joined together and decided to build observatory in South America, in Chile, in Atacama Desert. The first observatory was La Silla. It's working until now. There are many telescopes of various sizes in it. The newer one is called Paranal, from a mountain on the top of which it is located. And in Paranal, there is most complex optical telescope which is now in the world. It's a very large telescope, it's this name, or VLT, and it consists 4 telescopes of 8 meters each one, and 4 additional smaller 1.8 meter. They can observe sky individually, or they can observe together as interferometer. And interferometry is known from radio astronomy, but it is much more difficult in observing interferometry in interferometry with optical range. But in Paranal we can do that. And the third observing location is called Chajnantor. It's also in Chile, in Atacama. It's very high, 5,000 meters above sea level. And there is a network of radio telescopes there called ALMA. ESO is representing Europe in this project because ALMA is a more global project. And ESO is also building now a telescope of future, extremely large telescope, or ELT, which will be much, much larger than current largest optical telescopes. Nowadays, largest telescopes have about 10 meters in diameter, optical telescopes. ELT will have almost 40 meters diameter. It's like half of football stadium. So it will be very, very large jump in observational possibilities. So who knows what astronomers will discover with that. Many discoveries, also this really top discoveries you can know from media, were done with using ESO telescopes. Also, some discoveries done by Michaël Gillon also were done using ESO telescopes. So our today's guest is astronomer from Belgium. He works at the University of Liège, and his scientific research is about extrasolar planets. He's discovering them, he's analyzing their physical, chemical parameters. He's running a few projects, among them one called TRAPPIST, which is famous from TRAPPIST-1, so extrasolar system with many planets similar to in size and in mass to our planet. He also runs a project called Speculus, which also uses some ESO sites. Michaël Gillon was awarded a few prizes, a few awards, distinctions, not only scientific, but also, for example, from media. The Times magazine is for every year is announcing a list of 100 most influential persons in the world. And in one of editions, Michaël Gillon was also nominated to this list. So I think it's enough for introduction. let's allow Michaël to start his lecture.
Thank you very much for this nice introduction, and greetings everyone. I'm very pleased to be here today to have the opportunity to talk to you about habitable exoplanets and how science is entering into the realm of the search for life beyond our solar system. So, since I'm a kid, I'm fascinated by this kind of view. The stars in the sky fascinate a lot of people, and we see them as suns, which are very far away. But on my side, I also see them, since I'm a kid, as potential hosts for living creatures and maybe sentient creatures, civilizations. But it's just pure speculation. It has been pure speculation. It has been the realm of science fiction for long. But we are getting closer now to having science enter into this uncharted territory. Of course, you all have heard about the exoplanet field. You have probably a lot of you have seen this kind of artistic view. And I'm going to try to explain you how we're going to move from this kind of view, where you can see here a nice exoplanet with oceans and maybe life on it, to scientific answers. And yeah, of course, the question of sentient life in the universe is something else, something that it is tackled by another domain, which is called SETI, Search for Extraterrestrial Intelligence. And it's unrelated to my research. Well, it's related, but it's not what I'm doing. So I won't talk about it here. Okay. My story will start a few centuries ago, because I told you we know that the stars out there are suns very far away, light years away. But looking at the history of humankind, this knowledge is very, very recent. And it came with the so-called Copernican revolution, that started with everyone in Poland should know, Nicholas Copernicus, that proposed a new vision of the universe in the 16th century, with not the center as universe as the sun, but as the Earth, but as the sun. And so proposing that the Earth was not the center of everything, but just a planet, a so-called planet, orbiting around the sun like many others. And this revolutionary proposition was confronted to observations thanks to philosophers and first scientists like Galileo, Kepler, and others. And it was confirmed step by step. It was really the beginning of the scientific method that gave rise to so many knowledge that we have gathered since then. So now we have a clear view of our little piece of the universe, our solar system, our planetary system. We know that it's composed of this big ball of gas, very hot gas, with some nuclear fusion in the center, our sun. And it is orbited by 8 planets. Close to the sun, you have the 4 terrestrial planets. So you have Mercury, Venus, the Earth, then Mars in order of distance. Then further out, you have the giant planet. You have the very massive Jupiter. You have Saturn with its nice rings. And then you have Uranus and Neptune. And you have also many minor bodies, small bodies, like the belt of asteroids between Mars and Jupiter, comets. You have dwarf planets and so on. So we have a clear view of our planetary system, and we learn about it every day. But the question that the other stars could have planets is a very old one. And in fact, this question was already raised back at the time of, or a bit after the time of Nicholas Copernicus. Giordano Bruno was one of the first to raise this question. And in fact, he was the first to propose that the other stars could be suns, which was totally revolutionary. Even for Nicolaus Copernicus did not propose this. He considers the stars as kind of background, a cosmic background for our planetary system. But Giordano Bruno and others propose that they could be suns, but very, very far away. And Giordano Bruno went further out. He claimed that they had also planets around them, and even inhabited planets. And even the great Isaac Newton, that put into equation the dynamics of the solar system, notably, also proposed that the stars were also could be really suns with their own planets. But still, at that time, it was impossible to detect these extrasolar planets, what we call now exoplanets. Newton noticed it. Other physicists like Huygens also noticed that it was just impossible given the distance. The stars are so faint, they have to be, if they are suns, they have to be extremely far away, and it was totally unbelievable to be able to detect planets around them at that time. Now, I would like to go back to our solar system and to look at our planet, because it's a very special planet compared to the others. It is the only planet in our solar system that has water on its surface in liquid phase. So if you look at our Earth and you look at the small volume of water on its surface, it's really a tiny droplet compared to the bulk of our planet. But this droplet is super important because all forms of life on Earth, all our biosphere depends on water. Our cells, all the cells are mostly composed of waters. Water is really the key solvent, one of the key constituents of life. And so we call in astronomy habitable planet, a rocky planet that has liquid water on its surface. So far, we know only one, the Earth. Now, this kind of planet can't exist anywhere around a star. If we look at our solar system, we can define what is called an habitable zone, which is a range of distances for which, if you put liquid water on a planet like the Earth, it will remain in liquid phase. If you go too close to the star, it will evaporate. If you go too far away, it will freeze. And it will depend on the presence of an atmosphere. You really need an atmosphere around the planet to have enough pressure and to have a greenhouse effect large enough to sustain water in liquid phase. But even with an atmosphere, if you're too far away or too close, you can't have liquid water. So if we look at the habitable zone of our sun, you can see that Mercury is way too close to the sun. Venus is just at the inner edge, a bit too close. The Earth is right in the habitable zone, and Mars also is at close to the outer edge. So in theory, if we knew nothing about Mars and even Venus, we could maybe dream about life on Venus and Mars. But thanks to astronomy and then space exploration, we know very well these two planets, and clearly these are not habitable planets. They are completely different versions of hell. So one, Venus, is a kind of twin of the Earth in terms of mass, of size, but it is enshrouded by a very massive atmosphere, 100 times denser than one of the Earth, composed mostly of CO2, or carbon dioxide, with a super large greenhouse effect that translate into temperature on the surface that are close to 400 degrees Celsius and very high pressure, 100 times larger than on the Earth's surface. And furthermore, it's very acidic as a conditions here. So not a good place for life. And if we look at Mars, after some fantasies and dreams of Martian civilization, we now know that Mars has nearly no atmosphere. It's a super scarce atmosphere, 100 times less, well, scarcer than the one of the Earth. And with this super small atmosphere, it doesn't have the greenhouse effect large enough and pressure large enough on the surface to have water in liquid phase. And it has no magnetosphere also, so it's not protected from the particles coming from the sun and from the cosmos, the charged particles. So it's really a very inhospitable environment. Okay, so we have no choice if we want to find another habitable planet to look further out, to look beyond our solar system. And so what I show you here is, let's say, our piece of the universe, our local universe. We call it the Milky Way. You can see it in the sky when the sky is clear, far from light pollution. You can see a band that crosses the sky like this. And this band, in fact, it's Galileo that observes this band with one of the first, telescope, and that noticed that it was composed of plenty of stars. And now we know that if we could go very far from the sun and look back, we would see that the sun is part of a big cluster of stars, so mostly composed of stars, which is called the Milky Way, which is, well, in fact, we know that there is about 300 billion stars in this mega cluster, and they are all bound together by gravitation. And this is a kind of disk, so it's quite flat. It has spiral arms, so it's a very nice shape. If you see it from the top or the bottom, you can see it like this. Of course, we are not able to see our own galaxy because we are embedded in it. We can't see the Milky Way like this, but we can look at other galaxies and make this kind of images, and we know, thanks to the study of our environment, that our galaxy looks like this. So it's a very big place, plenty of stars, and the question is, do some of them have planets? Do some of them have habitable planets? So this question was very old, I told you, and it's surprising to notice that, in fact, the attempts to detect exoplanets are not recent. The first attempts were done in the 19th century. And notably, you have here a guy called Captain Jacob. He was a military astronomer, a British military astronomer who was based in India. And using the Madras Observatory in India, he was observing nearby stars, and he noticed that one of them had some peculiar motion in the sky. And he inferred from this motion that it was orbited by a planet. And so it was the first claim of an exoplanet discovery back in 1855. Unfortunately for him, this claim was refuted by more observation. And during more than one century, these kind of claims came back again and again. So astronomers claimed to have detected exoplanets, and then these claims were refuted. They were kind of optimistic in terms of the instrumental potential they had, in terms of precision they could reach with the instruments. And it was shown that, in fact, what they were observing was just noise, in fact. And now let's go a bit to the theory side, not to the observation. It's interesting also to notice that in the first half of the 20th century came a theory for the formation of our solar system that was based on a very peculiar event, a near collision of two stars. So when the sun was very young, it was postulated that it made a kind of flyby with another star that passed super close to it, and some material from one star was attracted by the other and was formed a kind of filaments that stayed around one of the two stars, around the sun, and formed at some point the planets. So this theory had an interesting consequence, because this kind of crossing very nearby, close encounter of two stars is something that is extremely unlikely, because stars are very far away in average from one to the other. We are talking about light years. A light year is 10,000 billion kilometers, so they are super far away. And you have a very tiny chance to have a star that gets so close to another one. So even with billions of stars in our galaxy, it could be possible that there is only one or a few planetary systems if they form like this. So at that time, many astronomers start to think maybe our planetary system is really something unique. Then later, after World War II, came another theory for the formation of our solar system. And the collision theory had some flaws, and at some point it was shown that it could not work. You could not form the planet this way. But then this new theory, what is called the core accretion theory or the disk theory, was much more interesting because it could really explain the global structure, the formation and the global structure of our planetary system. So the key postulate is that everything starts by a kind of a gas and dust cloud, what is called a molecular cloud. These things exist in the galaxy, there are plenty of them. And you can have a patch of this cloud that collapses under its own mass through the gravitational force. You have collapses of this patch of cloud, and it becomes denser and denser. The core becomes hot enough at some point and dense enough to sustain nuclear fusion and to become a star. So at this stage, it's a protostar. And the rest of the material will fall and will start to make a flattened disk around the protostar. And it will become denser and denser and flatter and flatter. And in this disk, you have the dust particles that start to aggregate, to collide, and to form bigger and bigger bodies. And you form pebbles, then rocks, then what is called planetesimals. You can still see these planetesimals in our solar system. They are called asteroids or comets. And then they accrete again, and you form planets. And if you're massive enough, you start to accrete the gas, and you form a giant planet. And it works very well, this theory, which was in fact the revival of an old theory dating from 2 centuries ago. And in the 80s, so not so far ago, it was confirmed by observations. It became a paradigm, thanks notably to the Hubble Space Telescope that was launched in the 80s, that observed plenty of nearby young stars, and that showed that if they were young enough, they were surrounded by plenty of material forming this speculated proposed disk, protoplanetary disk. So remains the question at that stage, is the formation of planets in this disk frequent or not? It was unknown. And of course, many believe it was frequent, but it was still to be demonstrated. And then came in the 90s, in 1992, a very big surprise, and thanks notably to a Polish astronomer, Alexander Wolfgang, and his colleague Frail, a Canadian astronomer, observing what is called a pulsar, a very exotic star. They could infer the presence of 2 bodies of planetary mass in orbit around this pulsar. But this discovery was important from a scientific point of view, but because of the exotic nature of the star, it didn't have a large mediatic impact. This was not yet the discovery of a planet around a sun-like star that was awaited, that had been awaited for so long. A pulsar is a neutron star. It is a corpse of a massive star. So massive stars have a very short lifetime, and they have a very catastrophic end. They end as a supernovae. So they explode, basically, the outer shells explode, are ejected, and you have a very high increase in luminosity of the object. And what will remain is a very dense object, which is called a neutron star, or a black hole. In this case, it's a neutron star, a very tiny thing, very, very hot. And so it was a kind of exotic star, and let's say the real discovery of an exoplanet around a normal star was still to be awaited. But the wait was not long, because it came 3 years after, thanks to these 2 Swiss astronomers, Michel Maillot and Didier Queloz. They detected the first exoplanet in orbit around a sun-like star. This discovery warranted them a Nobel Prize in Physics 2 years ago. And this was, again, a very big surprise, because the planet that they detected was a Jupiter-like planet, so a gas giant planet. But unlike Jupiter, which is quite far from the sun, this planet was super close to its star. So Jupiter takes 11 years to make an orbit around the sun. It is 5 times further out from the sun than the Earth. This planet takes 4 days to circle its star. So it's super, super close. So some astronomers were skeptics at that time, but it was confirmed. Many others were detected afterwards, and it was really the beginning of the exoplanet era, a brand new branch of astronomy that opened finally thanks to this seminal discovery. And to show you how dynamic this field has been since this historical discovery, you have here an histogram that shows the y-axis is the cumulative number of detection of exoplanets, and the x-axis is the year, in fact. So in 1995, you have the first planet around the Sun-like star. You don't even see it here. You see that during, let's say, a dozen of years, the rate of detection is relatively moderate, and then it accelerates, and it's nearly an exponential increase of the number of detections. And now we know more than 4,000 exoplanets around quite nearby stars. When I say nearby, they are all in our Milky Way and all in what is called the solar neighborhood. So, well, most of them at least are really in our local part of the galaxy. It's very difficult to detect planets that are in very far away. Okay. So, thanks to this large harvest, we can draw some statistical conclusions that are very important, and that basically change totally our view of the cosmos and of our own planetary system. So we know that planets are the natural byproduct of the formation of stars. So more stars in our galaxy, and by extension in the universe, have their own cortege of planets. That's totally normal. Nothing special here. But the planetary systems are very diverse, much more diverse than expected from the study of our own solar system. So we know that systems like our solar system, really twins of our solar system, represent something that at most 5% of the Sun-like stars. So it's really something that is quite rare. You have much more frequently systems that are very compact, like this one, where you have several planets of a few Earth masses. We call them, well, depending on their size, we call them super Earths or mini Neptunes, very close to the star. So you have on the upper left figure, you have an illustration. You have the orbit of Venus and Mercury, and within the orbit of Venus, for this system, you have 6 planets that are very close to each other around a star that is very similar to the Sun. You have the hot Jupiters, you have smaller planets that are also very close to the star, completely baked by the star. You have planets around 2 stars. You have planets that are in triple systems, so with 3 stars in the sky. You have planets around neutron stars. You have planets that have very elliptic orbits, so very elongated orbits, unlike the planets in our solar system that have orbits that are very circular. And you have also planets that are said free-floating, meaning there is no star at all. You just have the planet. These planets were formed in the protoplanetary disk and then ejected into the interstellar void. And we know that there must be something like 1,000 billions of them in the Milky Way, wandering between stars. Okay. And among these thousands of known exoplanets, there is a few dozens, a very select sample of planets that are said to be potentially habitable. Meaning we know they are probably rocky planets, terrestrial planets, and they orbit within the habitable zone of their star. So the next step in our study will be, our goal is to study in detail these planets, and notably to study the atmospheric composition to search for traces of life on these planets. This is very challenging, but we think we will be able soon to do it. Now, sorry for the text that is a bit shifted. It's due to the translation from PowerPoint to PDF. So I would like also to discuss about the methods of detection of exoplanets. So the most natural way to detect an object, an astronomical object, is to take a big telescope to make a high-resolution image. And to detect the faint object, you need, if it's very faint, you just need a bigger telescope. It's too faint for your telescope, you need a bigger telescope. And if you have a resolution large enough, you can discriminate between the 2 objects, which is the star and the planet. You can see the planet in your image, and then you can study the planet. So it's a very natural way, and it's also super challenging. So you have here the first detection that was achieved thanks to an ESO telescope, by the way, in 2005 of an exoplanet. It is the first image of an exoplanet, so it's a small red object close to the star here. It's a giant planet at the edge between planet and brown dwarf. Brown dwarfs are objects that form like stars but are not massive enough to sustain nuclear fusion. On the right here, you have the most illustrative and symbolic detection by this imagery method, the direct detection method. You have a system of 3 planets around the same stars. So you can see these 3 planets there, and you can see that the star is hidden. So there is it's dotted, it's blacked here, and I will explain afterward why. Okay, but first let me tell you what we want to do exactly. So in a simple way, what we want to do is to detect in our image a potentially habitable planet, to take the light of its object, and to do what is called spectroscopy. So spectroscopy is spreading the light of an object and spreading it in terms of wavelength, so in terms of color, basically. Just like a rainbow in the sky, the light of the sun is scattered in different colors. We can do this with an optical device, like a prism, and we can study for each color, we can measure the amount, the quantity of light. So what we call this the flux. So we can measure the flux at the different colors in the different wavelength, and we can see how it distributes. So it's shown here. So this figure shows what is called spectra, what you obtain by spectroscopy. The flux measured for Venus, the Earth, and Mars as a function of the color, as a function of the wavelength. And it is in a wavelength range, which is called infrared, to which our eyes are not sensitive to, and which is very rich in information about the composition of planets. And what you can see is that for Venus, you have a very flat spectrum, but at a given wavelength, you have a big drop of flux. And we know that this drop of flux, we know this thanks to physics, corresponds to a molecule which is called CO2. At this wavelength, CO2 interact with the light, absorbs the light. And so the light coming from the lower depth, from the lower layers of the atmosphere of Venus and from the surface, goes to the top, and a fraction of it will be absorbed by the CO2, and so you will have this signature in your spectrum. It's the same for Mars, except that for Mars, well, the scale is not the spectra are not at scale here in terms of flux, but the signature is very small because the atmosphere is very, very thin. And for the Earth, you have a more interesting spectrum because you have more signatures. You notably have a signature of ozone, which is a byproduct of the lysis of oxygen by the UV light from the sun, and you have a signature of water. And an alien observer that would get this kind of measurement from the Earth could be able to reach the conclusion there must be some interesting thing going on this planet. It's very possible that there is some biological activity because so much ozone has to come from somewhere. It should come from oxygen, and oxygen could come from photosynthesis. Furthermore, you have CO2 and H2O. All 3 together points towards a biological explanation. So we want to do the same thing, to get, by spectroscopy, the measurement of the composition of the atmosphere of exoplanets and reach maybe the conclusion there must be some life out there to explain this spectrum. And it's very important to know that life is not a neutral phenomenon. Life is part of the environment. It forms a biosphere. And this biosphere, it includes the upper layer of the Earth, including the atmosphere, the soil, and it's really a global system. So if you look at this tree, it pumps water through the roots, it absorbs the light from the sun during day through its leaf, it pumps carbon dioxide through the leaves from the atmosphere. The sunlight is going to be used to break the water molecule, and it is going to release oxygen in the atmosphere. And carbon dioxide, the carbon will be used to form bigger and bigger molecules that will form proteins, lipids, and so on, that are used by the tree to grow and to live. And so if we look at the evolution of the composition of the Earth's atmosphere, we can see a sharp increase of oxygen around 1 billion years ago, a bit less, because of the advent of photosynthesis. And because oxygen accumulated in the atmosphere, it reacted with everything it could. And at some point, there was nothing else to react with. And so oxygen started really to increase drastically in terms of abundance in the atmosphere. So this is really why we think that we should be able, even light years away, to study a planet and reach the conclusion there must be life out there. Because the same thing should happen out there, like here. Now, I told you about direct detection of exoplanets, so imagery. I told you that you need a big telescope to detect these planets because they are very far away, very faint. And so they are like this small firefly here. So it's very difficult to see the firefly with your eyes, but if you have goggles, you could see it quite far away. If you have, let's say, a telescope, you could see it even at kilometers away. But if it goes on a lamp house here, and you turn on the lamp, then you don't see anymore the firefly. It's totally lost in the glare of the much brighter lighthouse. And we have the same problem with exoplanets. They are always very, very close to the host star in the sky because their system is so far away. And stars are millions, if not billions times brighter than planets. So the problem is not resolution, the problem is contrast. But there is a way to get rid of this contrast problem, and it's basically very simple. You just have to hide the bright object, to hide the star. And this is something that is illustrated by nature in our solar system. We have the luck to have a moon, a big moon, and in fact the angular size of the moon is similar to the one of the sun. And when the moon passes in front of the sun, which is called a total eclipse, you can see the upper atmosphere, the very faint upper atmosphere of the sun. Outside the eclipse, you don't see it at all, just because the sun is so bright. We call this the corona, and it tells us about the magnetic activity of the sun, the magnetic field of the sun. It's very rich in information, but to observe it, we really need to hide the core of the sun. And we have the chance to have the moon to do it. For exoplanet, we don't, of course, have a moon that is ready to do the job. So there is some plans to develop very sophisticated and very costly also space mission where you would have an artificial moon, what is called a star shade. So you would have a space telescope out there, and you would have a second part to the mission, this star shade thing. So it's a kind of artificial moon, but with a complex shape to really decrease the noise from the star, to minimize it. That would be thousands of kilometers away from the telescope. And that would have to be positioned very, very precisely, so to hide the star, so to make possible to detect the planets that are close to it, that orbit around. This thing will make possible to detect habitable exoplanets and to study them. But this thing won't come before 2 to 3 decades, unfortunately. And because it's very technologically difficult and it has to be demonstrated, it will be a step-by-step process. So far, the only planets that we could image are giant planets very far away from their star, very hot, even more massive than Jupiter, much hotter because the systems are still young, and very far, much farther away from their stars than Jupiter from their star, from the sun, sorry. So we are still very far from detecting real Earth twins. But there is a shortcut. I think there is a shortcut. And I told you about this direct detection method, but it has only led to a few dozens of detections so far. Most of the exoplanets have been detected indirectly, not by making an image and seeing the planet in the image, but by observing the star and looking at the effect of the planet on the star. One way or another, it impacts our observation of the star, and we can infer the presence of the planet. Just like our invisible man here, you don't see it, but you see its shadow, so you know it's here, is here. So most of the exoplanets have been detected through a technique that is called planetary transit. So a transit in astronomy is when a small body passes in front of a big body. So it's very simple. It's pure geometry. And this is something that you can observe in our solar system because the Earth is a third planet from the Sun. The two inner ones, Venus and Mercury, have the orbit. It is nearly in the same plane than the orbit of the Earth. And so from time to time, you can see Venus or Mercury pacing in front of the Sun. So you have a transit, it is called a transit, of Mercury or Venus. In this case, in the image here, it's Venus pacing in front of the Sun. And you can see how Venus is tiny compared to the Sun. It's really, really tiny. For exoplanets, we can't make this kind of image where we see the planet pacing in front of the star. But what we can do, and unfortunately you won't see it in this fixed image, is that we can measure very accurately the brightness, the flux of the star. And we can do it continuously. And when the planet, if there is a planet and the orbit is well aligned compared to us, relative to us, when the planet passes in front of the star, you will have a drop of brightness, just because you have the planet that is hiding a part of the disk of the star. And we can measure this kind of phenomena because we are super precise in our flux measurements. And the amplitude of the drop of brightness that we will measure will directly inform us on the size of the planet. Because the bigger the planet, the more it hides the disk of the star, and so the dimmer will look the star when the planet passes in front of it. And so it tells us about the size. We know also that these transits have to happen once per orbit. So after one over revolution around the star, the transit happens again. So the frequency, the delay between two transits tell us about the orbital period. From that, using what is called Kepler third law, we can infer the distance between the star and the planet. So by using celestial mechanics, we can infer the distance between the planet and the star. And using other techniques, we can even measure the mass of the planet. So we have the mass, we have the size, we know how far it is from its star, we know if it's in the habitable zone or not of its star. We know, because we have the mass and size, we know if it's very dense like a rocky planet or low density like a puffy giant planet. So we can already say a lot of things about the planet. But we can even do better. We can do spectroscopy and study the atmospheric composition of the planet without seeing the planet at all. And indeed, when the planet passes in front of the star, you have the thin annulus of its atmospheric limb that will also pass in front of the star. And the atmosphere is not totally opaque. It lets some photons, from light coming from the star, pass through it. It will really depend on the composition of the atmosphere, on its properties. And so when we observe the transit, we will see a drop of brightness, but this drop of brightness will have an amplitude that will vary with the color, with the wavelength. Because if we observe in a wavelength that corresponds to, let's say, CO2, and if the atmosphere of the planet is very rich in CO2, then you will have an extra absorption of light from the star. So the limb will absorb a bit of the photons of the light emitted in our direction, and we will have an extra drop of brightness. And so by looking at the evolution with the wavelength of the drop of brightness, we can measure what is called a transmission spectrum of the atmosphere. And we can really infer the properties of the atmosphere and its composition. Basically, the light is emitted in our direction, a fraction will pass through the atmosphere, and it will be filtrated by the atmosphere, and we are going to detect this filtration. It's very challenging, but it has been done for plenty of giant planets. Now we would like to do this for habitable planets. A giant planet like Jupiter is 10 times larger than the Earth. An Earth-like planet, you can see how small it is compared to the Sun, and we would like to detect not the planet itself, but the tiny fraction of light that pass through the thin annulus around, atmospheric annulus around the planet. This is not possible if the star is so big, because this fraction of light emitted in our direction that will pass through the atmosphere will be super, super tiny. We're talking about something like 10,000 of a person, which is not detectable. But there is a very simple solution. Oh, sorry, it does not appear here. So you should see on the right, what you should see is a tiny star. And indeed, this is the logical solution. If your star is too big, go to smaller stars. And fortunately, most stars in our galaxy are much smaller than the Sun. They are called red dwarfs, these small stars. And the smallest red dwarfs are called ultra-cool dwarf stars. They are really, really small. They are as small as Jupiter. So Jupiter is 10 times bigger than the Earth, but the Sun is 100 times bigger in terms of diameter than the Earth. So you have a factor 10 between the smaller star and the Sun, and it translates into a signal which will be 100 times larger and detectable with current technology. So if we want to study small planets and potentially habitable planets, we have to move to small stars. And to do this kind of challenging studies, well, it has been attempted from the ground, it has been attempted with the Hubble Space Telescope, but there is no result for these kind of planets because it's really too challenging. What we need is a very big telescope. We need it in space to get rid of the perturbation coming from the atmosphere of the Earth. We need also a telescope that operates in the infrared wavelength range, because this is where most of the information on the atmospheric composition lies. This is really where most of the signature we are looking for lie. So we need this kind of telescope. So far, it hasn't existed, but it exists now. It is nearly ready to be launched. It is called the James Webb Space Telescope, and it will be launched at the end of the year, so next month, normally it's December 18th, from French Guiana. And it's so big, this telescope, it is the biggest space telescope ever. It's so big that it can't fit into its rocket. So it is an Ariane 5 rocket, so a European rocket that will launch the telescope, and it has to be folded in the Ariane rocket, and it will unfold in space, deploy, and then it will start to operate. This deployment will take a few months. You will have also the commissioning of the instruments. So around, let's say, May, June 2022, the telescope should be ready for operation. And then we will have the perfect tool to study the atmosphere of small planets around small stars. But there is also an extra challenge. Of course, James Webb is going to be launched, but we need projects that find these kind of planets. And there are two main projects that do the job. One is an American project. It is called TESS. So TESS is 4 tiny telescopes, 10 centimeters. So it's really, really small telescopes. But they have an advantage. They are in space. So they are stuck to a satellite, which is orbiting the Earth. And the TESS is observing with these 4 telescopes, basically the world's solar neighborhood. So around 2,000 targets that are very nearby in our galaxy. And it's not able to detect potentially habitable Earth-sized planets, but it should be able to detect bigger planets around stars that are a bit bigger than the ultra-cool dwarfs that I mentioned. So what are called super-Earths. And some of them, for what we know, could be habitable. And then we have a European project that I have the chance to lead, which is Speculoos. It is not a space project, it is a ground-based telescopes. It is a network of ground-based telescopes This project is led by Liège, and it also has 4 other institutions that are part of it. So it's a much cheaper project. It started around the same dates and tests. It has much less targets, only 1,000, 5,000 targets, but they are the smaller stars in the solar neighborhood. So these are stars that are out of reach of tests, and these are the stars that we believe are the best targets to find Earth-sized planet well suited for detailed study with James Webb. Okay. And by the way, Speculoos is a reference to a cookie that we are a fan of in Belgium. And before launching Speculoos, we wanted to do a prototype for Speculoos to convince our sponsors to fund our project, because 7 million euros, it's the cost of the project. It's not easy to gather this amount of money. So we decided to use our robotic telescope TRAPPIST. So TRAPPIST is a telescope that belongs to Liège. It's located in Chile on the Iso La Silla site in the Atacama Desert. It has been installed there in 2010. So TRAPPIST is a reference to TRAPPIST beers, if you didn't notice. Also something we are very proud of in Belgium. And TRAPPIST is dedicated half of its time to the observation of transits, of exoplanet transits. And from 2011, I decided to use it as a prototype for Speculoos, observing a small sample of stars. And so in 2015, the prototype gave an amazing discovery. It gave this signal here. So it doesn't look so amazing to most people, but what you see here is the evolution of the flux of one of our targets during the night. And you can see a drop of brightness that corresponds exactly to what you would expect for an Earth-sized planet passing in front of the star. And with more observation, notably thanks to ESO telescopes, we could confirm this planet and other planets. And in fact, it was totally crazy because planets were coming at very high speed. We had 1, 2, 3, 4 planets. It was really a kind of nightmare to solve the system because we had so many planets. So just to outline how small is TRAPPIST-1, so we call the star TRAPPIST-1 afterward. So TRAPPIST-1 is 40 light years away, which is really super close at the scale of the galaxy. And it's as small as this compared to the sun. So it's 10 times smaller than the sun. If you would put Jupiter next to TRAPPIST-1 and the sun, you would have the same size for TRAPPIST-1 and Jupiter, basically. Okay. And thanks to the very large telescope, in 2015, we observed something that was really spectacular and that told us that this system was even more unique than what we thought. So at that time, we knew that there were 2 planets and probably 3. And then we observed this weird event. So you have, again, the flux that evolves as a function of the time during the night. And you can see that there is a big drop of brightness, then a small one, then you have an increase of brightness, another one, then another one. And the only way to understand this variation is to assume that you had 3 planets of the size of the Earth that passed at the same time in front of the star. And 2 of them at that time were unknown to us. So we knew that there were 4 or 5 planets in the system. And then at that time, the star was not visible anymore. At the end of 2015, we had to wait for it to come back in the sky. So it was in the sky, of course, but it was behind the sun, so we could not observe it. And in spring 2016, it came back. We observed it from the ground with ESO telescope again. And then we knew that there were more planets. There were 5, 6, 7, we didn't know. So we had to go to NASA and to ask them to use the space telescope Spitzer, an infrared space telescope, much smaller than James Webb, but very capable. And we observed continuously the system for 3 weeks, and we observed 34 transits. And combining all this data and this transit observation to the one we had before, we could crack the system, and we could infer that there were 7 planets in this system, all of them with a size similar to the one of the Earth. And furthermore, because we knew the distance to the star, we knew the amount of light they receive from the star, we knew that 3 of them at least were in the habitable zone of the star, which was totally also unique and completely crazy. And in fact, even the 3-4 others are close enough to the habitable zone to have maybe, you have the possibility to have some liquid water on the surface, on a fraction of the surface on these planets, depending on the atmospheric composition and so on. So this system is really completely crazy in terms of habitability, potential habitability. And furthermore, this is the very best system, the dream system for a study with the James Webb Space Telescope. So if you could go there, we can't, of course, go there, but if you could go there, the show should be amazing on the surface of this planet. The star, because these planets are super close to the star, we are talking about distances of a few percent of the Sun-Earth distance. So the star is 10 times smaller than the Sun, but the planets are so close, you should see the star around 10 times bigger than we see the Sun in the sky. So it should be a huge thing, but quite dim, because the star is very cold and very dim. So you could be able to watch, to look at the star without burning your eyes, at least when there is no activity on the star. And the planets, you should see them like we see the moon. So you should see the details on the planet. When you look at Venus or Mars, it's a pretty disappointing because you don't really see, you just see a dot of light. Here you would really see the structure of the planet, what is on the planet, I don't know, clouds, oceans, I don't know. Whatever is there, you would see it just by using your eyes. And furthermore, the star is so cold, it emits basically only red and infrared photons. So everything should be very reddish. You wouldn't see any blue, green, just black and red, which should be very alien. Also, the planets are so close to the stars, they should be what is called tidally locked, meaning they should show always the same face to the star, like the moon to the Earth, because of the tidal influence of the star. So you should have a day side, which is permanently day side, which should be hotter than the night side, which should be cooler, always in the dark. And in between, you could have a pleasant part of the planet. It really depends on the atmospheric composition and its density. And also the star is small, but it's also, like all these tiny stars, it's quite a temperamental star. So it has a large magnetic activity. From time to time, you have what is called a flare, so a kind of explosion on the surface with a large amount of X-ray, UVs that are emitted. And this could be harmful for the atmospheres of the planets, depending on the replenishment of the atmosphere, depending on the protection of the atmosphere, you could lose quite quickly the atmosphere or not. For what we know, there could be an atmosphere, but it's also possible that there is no atmosphere at all. If there is no atmosphere, then the habitability of the planet is not possible, unfortunately. But we will have an answer to this. We will know if there are atmospheres thanks to the James Webb Space Telescope. And yeah, NASA made a large noise about this discovery because that was really the dream target for James Webb. So many people at NASA were super excited to see such a dream system being detected for the big telescope. And this is the kind of things that James Webb should be able to detect. So it's what is called a transmission spectrum, a transit transmission spectrum. I'm not going to explain the detail, but what you can see is that there are structures that we could relate to molecules like methane, CO2, ozone, and so on. And some of them could be related to biological activity. So we have now some opportunities to hunt for life beyond our solar system, thanks to TRAPPIST-1. Now, I would like to finish with the project Speculoos I mentioned. We detected with the prototype TRAPPIST-1, but Speculoos now is operational. Our core facility is on the ESO site of Cerro Palanal in Atacama Desert. That was already presented before. So you can see how dry the place here is. These telescopes are not on Mars, they are really on Earth. But the Atacama Desert is the driest place on Earth. So it's super dry, it's high altitude, there is nearly no turbulence. The sky is very, very clear, nearly no light pollution. clouds are very rare, and it's really the perfect place for astronomy. We have one telescope also in Tenerife, in Canary Island, and one in Mexico. Okay, let me show you a nice image of the sky, the southern sky, as you can see it in Cielo Palanar. So this is speculoos telescopes in observing, and you can see that, well, you see the Milky Way, you see some galaxies, you see it's a super clear sky, so you can make amazing images, even with a small camera, and it's really the dream for astrophotographers to go there, because it's a magic place. Thanks to COVID, I haven't been there for 2 years. I'm looking forward to going back to Chile to have this kind of view again. And here you have a view of speculoos telescopes, the 4 speculoos telescopes. And you have here the very large telescope that was mentioned before by Christophe. And here you have another European telescope, which is called Vista. And we have also a very nice view on this mountain here from speculoos. This mountain is Cerro Amazonas. This is the place where is being built extremely large telescope that was also mentioned by Christophe, that will totally revolutionize astronomy thanks to its, well, amazing size. So this is Speculoos North in Canary Island. This is a Teide volcano. We hope that it will never wake up. You know that at La Palma there is some volcanic activity now. We hope that at Tenerife it won't happen, because it would be a bit disturbing for us. And this is Syntex telescope that is located in Mexico, in San Pedro Martir in Baja California. And I'm glad to report that after more than a year of observations and after some interruption due to the pandemic, we have our first speculoos system detected. So we don't call it speculoos 1, we call it speculoos 2, because TRAPPIST-1 was detected in the framework of speculoos, so we call it also speculoos 1. So this system is still under study. Today I had a note from my team that noticed another transit from a planet of the system, so it's going to be amazing to study this system and to see how it compares to TRAPPIST-1. And I would like also to mention that, okay, we are living in the James Webb era. We are close to open this James Webb era, but the future is very bright for exoplanets, not only thanks to James Webb, but also thanks to the giant ground-based telescopes that will notably make possible to detect by direct imagery at some point potentially habitable planets larger than the Earth, and after some developments, maybe 1 or 2 decades from now, similar to the Earth. It will be difficult, but at some point it will be also possible for a few nearby stars. And to detect a lot of them, we will have to wait for the space mission I mentioned with the Starshade. One of them is called ABEX, and it is in preparation. It is in design phase in the US. And we hope that at some point it will be a reality. And until that, I can tell you that, well, we are all fascinated by the possible existence of life beyond our solar system. The answer to this question could enter the realm of science very, very soon. And maybe within a decade, we could have first pieces of answer. And I thank you for your attention.
Thank you very much for excellent talk. We have a few questions here in a quick meeting and also at YouTube. For example, Piotr Perliński is asking that methane is also one of the potential markers for biological processing. Could you say something more about that?
Yes, indeed. So methane is a molecule that can be produced by some bacteria on Earth that are called methanogenesis, and it could, in theory, accumulate a lot in the atmosphere, notably before what is called the Archean Earth. So in the first phase of life on Earth, some argue that we could have had some large amount of methane in the atmosphere. But methane reacts a lot easily with oxygen. So when you start to have oxygen, it reacts a lot and it basically disappears. But this is also very interesting because you could have a planet for which we have a detection of methane and oxygen. And as methane has a very short lifetime when you have oxygen, the fact that you detect methane in large amount means that you need a very large source of methane. And there are not so many abiotic, so natural sources of methane except life. So if the amount is large enough, we could reach a conclusion there must be some biological activity producing all this methane if we have this kind of combination. So what we are really searching for in this atmosphere is called a chemical disequilibrium. So when you have different molecules that react strongly with each other in large amounts, and that you should not observe this mix, this composition without large sources on the surface, and so large that they can only be biological.
There is a question from Bogdan. It's quite long. Talk about life on planets in Polish Omega popular series of books in early 60s. I was reading about something like this. We have now much more data about this subject, especially exoplanets, but I have impression that there is not any breakdown in speculation about life there. In our thinking, we cannot unplane from the water as a basis of life. Organized energy consumping, self-replicate, and evolving. Can it be water independent?
Okay, so the question, I didn't get everything, but the question is about the need for water, right?
Yes, I think the question is about if life can be water independent.
Well, in theory, yes. Some scientists have argued that you could have other solvents that could play the role of water, but water is really a kind of magical molecule because it has really peculiar features that you don't find in these other candidates. And notably, it is a polar molecule, so it has a positive charge and a negative charge that make possible to form complex structures, to trap some molecules in a given state. But this trapping is soft. You can have the molecules that can change shape quite easily, just like our enzymes. So biological molecules need some flexibility, the possibility not only to be big, but also to change shape, to adapt, to change the morphology for the activities. And this is something that water permits. For instance, if you take methane, methane is also a simple molecule that could be quite abundant in some environments. It can be liquid, notably it could be liquid on Titan, which is a moon of Saturn. But to be liquid, it has to be at a very low temperature, super low. And at such low temperature, chemistry is very, very slow, which is not a good thing for life to maintain sufficient activity for its existence. And furthermore, methane doesn't have all the features of water. It permits the existence of quite long molecules, but they are very rigid. So they don't have the versatility that we know that we need for life as we know it to exist. So we can think about other candidates, but I think that water is our main candidate, and it makes real sense for exoplanets to follow water, because we can't go there, we can't really make super detailed study and search for weird metabolisms that would not use water. We can just get the light that we receive from the system and get some information from it. So looking for water makes really a lot of sense. In our solar system, when we go on Titan, for instance, we can be a bit more open-minded, but not for exoplanets, because we are stuck in our solar system and we have to take what we get.
Question from Janusz Petkowski. TRAPPIST-1 system planets are truly remarkable. Do we have any indication that systems like TRAPPIST-1 are common, or are they unique?
Well, this kind of system, we can already get some statistical constraint on the existence of these systems, because we have observed for 2 years with speculoos, and we don't have a twin of TRAPPIST-1 detected. So it indicates, even if it's still small number statistics, that this kind of system is quite rare. And if we look at systems around more massive stars that are more known, because there is a large sample of them known, thanks notably to the Kepler mission, this kind of system, when you have planets so close to each other, many planets, is quite rare, because the planets are, to be so close to each other and to make a stable system, they have to be in what is called resonance. So the orbits have to be related by integer ratios. And this kind of resonance system seems to be very rare. During the process of formation of planet of similar system, generally you have some chaotic phase, and some planets are ejected, and at the end you end up with a different system with planets that are a bit further out from each other. And this kind of super compact system seems to be very rare. So we can expect the same, even if the answer is still not totally clear, but we can expect that TRAPPIST-1 is a rare beast, that we are very lucky to have it so close.
Piotr Perliński is asking, can we use for searching exoplanets also radio telescopes?
Could you repeat?
Could we use also radio telescopes for searching for exoplanets?
Well, no, not really. We could, well, for radio telescope can be used to study the magnetic activity of stars, and we could maybe think about perturbation coming from the magnetic field of the planets, but it would have to be a giant planet with a super large magnetic field. Else you wouldn't detect anything for an Earth-like planet. So it's not the best, the most promising wavelength range to detect planets. No, certainly not. Still, the planets around the pulsars have been detected by radio astronomy using the Arecibo telescope, but it was a very peculiar object. A pulsar is a neutron star in which we have the magnetic axis that is tilted compared to the rotation axis, and you have basically the magnetic poles emit light continuously, but because of the rotation, super fast rotation, you have a beam that is rotating, and at each rotation you have the Earth that fall within the beam. And this kind of object can be observed, studied in radio waves. And what was detected, the planets were detected because the period of the signal was changing continuously because the system, because of the planets that are orbiting around the system, the star it's also orbiting around the common center of mass of the system. It has a tiny motion, it is perturbed by the planet, and so you have some delays in the signals. But it's really something extraordinary. This is not the mainstream way of detecting exoplanets, and I think it will remain an oddity.
How can we detect planets that do not orbit any star?
Oh, so you have two ways. One is, again, the most logical one is to take a big telescope, and then in this case you don't have any more a contrast problem. You just need to point at the right place and to detect a super faint object. But the problem is that a planet that is not orbiting a star gets cold very, very quickly, and it can be nearly as cold as the interstellar void. So it's near 0 degrees. So it's near 0 degrees Kelvin. So it emits nearly nothing. So it gets very difficult. You need a planet that is free floating, but also it is still young and still relatively hot to be detected. So there are at least two candidates, but we are not sure if they are planets or not. But there is another method, which is called the microlensing technique. So you're using general relativity with this technique. So general relativity, so the gravitation theory of Albert Einstein, says that a massive object deflects the light passing close to it. So light is deflected, and you can have a source which is very far away, let's say close to the galactic bulk, or giant stars that emits a lot of light. And you can have between this source and us, you can have a system, a planet or a star that pass in front of it. You won't have any transit because it's another effect that you will detect. It's the lensing of the light emitted by the source. So you will the planet or the star will play the role of a lens. It will collimate. It will focus the light from the source to the Earth by chance, by pure alignment, by pure. It's a super rare event, but it has already been detected. So there are some projects that observe the center of the galaxy, which is a very dense part of the sky, plenty of stars, and for which, if you observe long enough, you have the largest chance to detect this kind of thing. So you have a magnification, an increase of the apparent flux of the source, and by studying this increase of the flux due to the focusing of the light to the Earth, you can infer the mass of the object that has deflected the light. And for some objects, we have masses that have been measured that correspond to planets and not stars. And so by using then a statistical analysis, we know the probability to catch this kind of event. We can infer from these probabilities and the number of events, the amount, the number of planets out there that are free floating in the galaxy. And this was done.
There is also a question about spectroscopy. If we have tidally locked planet, where only a small part of a planet will contain liquid water, will it be easier or harder to detect water in spectra?
Oh, that's a good question, because with the transit technique, we are really probing only the limb. So if you have an inhomogeneity on the atmospheric composition, and you should have at some extent, you could have observations, a composition that is inferred that is not representative of the whole planet. So notably, if you have a dense atmosphere, you can have the day side that is very hot, and the heat has to go somewhere, and it goes to the night side, so you have very strong winds. And these strong winds will impact the composition. So you have motions in the atmosphere, you have a global dynamics that can be very strong, and you could observe a part of the planet, the limb, that is really not representative of the day side or night side. So you could have liquid water on water that is very abundant on the night side, and you wouldn't detect it. So it's indeed possible. This is why we use, and it's very important for this kind of planets, we use models that are called CGM models. So these are 3D models that take into account the dynamics of the climate of the planet, the irradiation, but also the 3D motion in the atmosphere. These models were developed for the Earth to study the weather, to predict the weather, the meteo. But we use them now for exoplanets, and it's very important for tidally locked planets to predict and interpret the observations.
What constraints are there to send a probe to an exoplanet?
Could you repeat?
What are constraints to send a probe to an exoplanet?
What are constraints to send a probe?
Yes, to send a probe to an exoplanet.
Well, sending a probe, in situ study of exoplanets. Well, this is something that is totally outside the realm of our current technology, unfortunately. So there is one project that wants to do it, which is called Breakthrough Starshot. So the idea is to send nanochips, so super tiny chips that will, one way or another, do a measurement, and to use a very powerful laser to accelerate them to a speed which is similar, let's say 30% the speed of light, to reach the nearest star within 10 to 20 years. But the problem is that it's only a concept, so they will be pushed by the radiation from the laser. You need a sail to do this, what is called a solar sail. So it's something that reflects perfectly the light. And by action-reaction, by reflecting the light, by sending back the light, it is accelerated in the other direction. But in theory, it could work. In practice, it doesn't work. We don't have the material to make this possible. We don't know how we would be able to study the planet with a tiny thing of a few grams and to send back the observations to Earth. So basically, it's pure science fiction so far. To really send a probe out there, something that has the capacity to study an exoplanet in detail, you would need to master at least nuclear fusion, and you would need a budget that is similar to the budget of humanity for 1 year. So we are not there yet.
I see that Marek is on, so I think we are closing to the time to finish. So thank you very much for answering questions.
Okay, Krzysiek, thank you very much for moderating this part. Michaël, thank you so much for answering all the questions, and many thanks for delivering this lecture. May I have my own question? I mean, what would be your dream as a researcher in terms of the technology or in terms of the instruments that would allow you to discover even more extrasolar planets or exoplanets?
Oh, my dream now would be to have the James Webb Space Telescope only for myself, if it was possible, because really it's a perfect tool, but the problem is that the competition will be very large to have access to James Webb. So in the first cycle of James Webb, TRAPPIST-1 will be the most observed system, planetary system. But we know that to really enter into the enter into the atmospheric composition of the planet, to learn about them in detail, and to learn about the planet that we are going to find with speculoos, we will need thousands of hours on James Webb. It's going to be very hard to have such a large amount of time, and James Webb has only a lifetime of 5 to 10 years, so that's going to be very, very challenging. So a mission like James Webb, but totally dedicated to exoplanets and not to global astronomy in general, that would be amazing. But this is the concept of ABEX, LUVOIR, future missions. But unfortunately, I think I will be retired when they will exist.
I will be keeping my fingers crossed for your allowance of the time for James Webb, if possible. So if you need it, let's keep our fingers crossed and back the idea. Thank you so much, and I'm really grateful for accepting again this invitation to A+ lectures of Pomeranian University in Słupsk, Poland. Krzysiek, thank you so much for moderating. ESO, I mean, has a big part tonight, and we're really grateful that we could take part in that event. Astronomy is something I'm very interested in myself, and I can tell by the chat box, by the number of questions, and then people also answering those questions themselves, I mean, in between themselves, that the heated debate is going on online, and that this event has sparked interest, which really is something we wanted to achieve. We also have lots of thank you notes coming in through chat and also through YouTube chat. So thank you, Michaël, for this event, for this lecture, for giving us, sharing your time with us. And I would like to invite all of you to another A+ lecture, and it's going to happen in 2 weeks' time. It's going to take place on the 16th of November, and we will have a guest from Harvard University Medical School, and it's going to be on medicine. So, stay tuned for our invitations. Stay tuned for links, for YouTube channel links and Click Meeting links. And thank you. Good night. Goodbye. Have a great evening, everyone. You have some food for thought, I hope, to sleep with. And goodbye. Good night. Thank you.